Have you ever really stopped to think about what's going on inside your phone or your laptop? I mean, we use them all day, every day, but how they actually think? It kind of feels like magic, right? Well, today we're going to pull back the curtain and demystify the core ideas of computer science to see what's really happening under the hood.
So at its most basic level, every single computer program does the same exact thing. It takes an input, a click, a word you type, a photo you take. It processes that inside what we call a black box, and then it gives you an output, a like on a photo, a search result, whatever. The big mystery, the thing we're going to crack open today, is what is actually going on inside that box.
All right, to understand that black box, we have to start with the language it speaks. And you might be surprised to hear, it's actually a really simple language. It's just a language of on and off, yes and no, 1 and 0. For our purposes, let's call it the language of light bulbs.
The absolute smallest piece of information a computer can understand is called a bit. The easiest way to think about it is like a single light switch. It can only be in one of two states. It's either off, which we call a 0, or it's on, which we call a 1. That's it. And get this. Inside your phone, there are literally billions of these tiny microscopic switches called transistors flipping on and off all the time.
So, to make this whole thing easier to wrap our heads around, let's just imagine that each one of those bits is a simple light bulb. Now, a single light bulb by itself isn't super useful, right? It can only be on or off. But what happens when we start adding more light bulbs? This is where it starts to get really cool. With just 3 light bulbs, we can suddenly represent 8 different numbers. Think of it like this. The bulb on the far right is the 1's place. The one in the middle is the 2's place, and the one on the left is the 4's place. So, if they're all off, that's 0. If just the 1's bulb is on, you get the number 1. If only the 2's bulb is on, that's the number 2. By combining them in different patterns, we create this whole counting system called binary. And here's where it gets really powerful. If we group 8 of these bits together, which is what we call the byte, we can suddenly represent 256 different values. We can make any number from 0 all the way to 255. Think about that. We started with a simple on-off switch, and now we've built a way to express a whole range of numbers.
Okay, this brings up a pretty logical question. You're probably thinking, that's great for numbers, but my computer isn't just a calculator. How do we get from 1s and 0s to sending a text message, or seeing a picture, or using an emoji? How does a number become, well, an idea?
Well, the answer is surprisingly simple. We all just agreed. We created rules, or standards. For example, there's a standard called ASCII that just maps numbers to letters. The number 72 means a capital H, the number 73 means a capital I. For colors, we use 3 numbers for red, green, and blue. And for the thousands of emojis, there's a massive standard called Unicode that gives every single symbol its own unique number. It really is all just numbers under the hood.
Okay, so now we have the language of the computer, binary. We've got the ingredients, but knowing the ingredients doesn't make you a chef, right? You need a recipe. You need to know how to give instructions. And in the computer world, that's where we get to the power of algorithms.
An algorithm is just a fancy word for a recipe. It's a very precise, step-by-step set of instructions for solving a problem. Everything from sorting your email to finding the fastest route on Google Maps, that's all powered by algorithms. They're the brains of the operation. But here's the thing, not all recipes are created equal.
So let's imagine a classic problem. Let's say you have a massive, old-school phone book, and you need to find one person's name in it. How would you do it? Because whatever method you choose, that's your algorithm.
Now, one way to do it is to just start at page 1 and read every single name, one by one, page after page. This will absolutely work. You'll find the name eventually. But man, is that slow. It's correct, but it's incredibly inefficient.
Now, let's think about a much smarter way. What if you open the book right to the middle? Then you ask a simple question. Is the name I want in the first half or the second half? Based on that answer, you can literally just toss out half the book. Then you do it again with the half that's left. You just keep splitting the problem in half, again and again, until you've zeroed right in on the name. And this graph shows you exactly why that difference matters so much. That red line shooting straight up, that's our slow, page-by-page algorithm. As the problem gets bigger, the time it takes just explodes. But look at that green line. That's our smart, divide-and-conquer algorithm. It's dramatically more efficient. And this is why computer scientists are so obsessed with finding better, smarter algorithms.
So,
we have our language, binary, we have our recipes, algorithms. Now, how do we actually translate our ideas into instructions that a computer can run? Let's make this really tangible with a fantastic tool called Scratch.
You know, before programmers write actual code, they often sketch out their recipe in something called pseudocode. It's basically a draft of the program's logic, but written in plain English. It's a way to organize your thoughts before you get bogged down in all the specific syntax and semicolons of a real programming language.
And here is where it all just clicks together. Look at this. On the left is the pseudocode for our phone book search. Notice that if the person is in the first half, else, logic. Now look to the right. That's a block from Scratch. It is the exact same if-else idea, just turned into a visual block that you can snap into place.
And that's the whole beauty of Scratch, which is a visual programming language from MIT. Instead of typing out lots of complicated commands, you just snap together these colorful blocks that represent different programming concepts. It lets you focus on the logic, on the recipe itself.
All right, so let's try to solve a quick problem in Scratch. Let's say we want this cat character here to meow 3 times. How would we write the recipe for that?
Well, our first instinct might be to just grab the play sound meow block and stack it 3 times. And you know what? Just like our slow phone book search, this works. It's correct, but it's also pretty repetitive and clunky. You just know there has to be a better way.
And of course there is. A much more elegant solution is to use a loop. We can grab this one repeat block, tell it to run 3 times, and then just pop the meow block inside. It gives us the exact same result, but the code is so much cleaner and more efficient.
But we can take it one final step further. We can create our own custom block and just call it meow. Now, this is a profoundly important idea in computer science called abstraction. We've taken a whole process, bundled it up into a single, simple, reusable idea. Now, we don't need to worry about how it works, we just need to know what it does.
And with that, you have just learned the fundamental building blocks of all of programming. Seriously, you have representation, turning ideas into ones and zeros. You have algorithms, creating those efficient recipes. You have conditionals, that if-else logic for making decisions, loops for doing things over and over, and abstraction for simplifying all that complexity. This is your toolkit.
So you see, that black box isn't really magic after all. It's just a combination of these simple but incredibly powerful ideas all layered on top of each other. The real magic is in how you choose to combine them. Now that you've peeked inside the box, the only question left is, what recipe will you write?